not sure that all, but some. Or at least how I view them. So I'm not sure that at the end of the talk you'll know more about garbled circuits, but you'll know more about the way that I think of them. Okay, and I forgot to say, I want to thank the organizers for organizing this wonderful event. So we'll start with the definitions and the properties, and then I'll talk about basic feasibility results about garbled circuits. So I'll show you a new way to reprove like the basic old results that most of us already know. Then I'll try to cover the recent efficiency improvements. So there have been a lot of work in the last few years. I'm not going to cover all of it, but at least some. And unfortunately, I'm going to skip the practical advances. So Yuval mentioned it. On the practical side, on the side of implementation, people did a lot of work in optimizing the concrete efficiency of garbled circuits. And as I understand, we'll hear about it in the MPC workshop. So, and finally, if we'll have time, I'll say a little bit about the applications. But I'm going to focus on the object itself rather than its applications. Okay, so garbled circuits were introduced as many other things by Yao in the mid-80s. And it's a powerful cryptographic techniques with a very large number of applications, very different applications, like we already heard from Yuval about constant round secure computation, but also for parallel cryptography and one-time programs, KDM security, you know, and even hot topics, recent topics like functional encryption and bootstrapping obfuscators, things like this, use garbled circuits inside. And the first question is what is a garbled circuit? And indeed, our view of garbled circuit has been changed over the years. So originally, when Yao presented them, we thought about them as a secure two-party protocol. And later, Fege, Kilian, and Naor kind of thought about it, showed that actually you can think about them as a protocol with minimal interaction. So, you know, it's a one-round protocol or private simultaneous message protocol. And later, Yuval and Eyal took another step and thought about it as a standalone object. So this is what is called randomizing polynomial. So as the name suggests, this is studied in algebraic framework. And we later extended this notion, threw away the algebra and just thought about it as a randomized encoding of functions. And finally, recently, Belar, Hong, and Rogoway gave their own abstraction of a garbled circuit, a garbling scheme, which is kind of has more, it's formulated in a more cryptographic flavor, like a tuple of algorithms and so on. And so we have many different ways to think about garbled circuits, and in fact, it's very useful to think about it in different ways, and each way has its own advantages. So for me and for this talk, I'm going to think about a garbled circuit as a way to encode a computation, encode a function, or maybe to encrypt a computation. So what does it mean to encrypt or to encode a computation? So you have your function which takes x and outputs y, and I want to have a new function, g, which encodes in some sense the original function. So in what sense? I want that when you give it an input, the same input x, the output will be an encoding of the output of the original function. And when I say encoding, I mean like encoding, you know, this is innocent encoding. It's not cryptographic in any sense. So it means just means that given this thing, you can recover y and vice versa. So it's just a representation of the original output. Okay? And to make life interesting, I'm going to allow G to use some randomness. So G is a randomized function. Okay? So it takes random coins. Alternatively, you can think about it as taking two inputs, the deterministic inputs, and the second input, which is usually going to be chosen uniformly at random. So now we can think about the output of G as a distribution, as a probability distribution. Right? For every x, I can define the distribution, the output distribution of G, which is induced by choosing this string uniformly at random. And I want this distribution to encode the string. Okay, so this is somewhat weird. The distribution encodes the string. So what does it mean? It means what it meant before. So given a sample from this distribution, I should be able to decode this value, and vice versa. Given y, I should be able to sample from this distribution. Okay? So formally, I'm thinking about, so this thing is the randomized encoding of the function f. And I'm thinking about two properties. Okay? So this is the formalization of what I just said. So there should be an efficient decoding algorithm, which given a sample from this distribution gives you the y. Okay? So for every x and every r, if you apply the decoder to g of x and r, you should recover the value f of x. And as you can imagine, you can also relax this notion and ask for it only with high probability or allow some error probability. For this talk, I'm not going to talk about it, so correctness is always perfect. And the second property is what I call privacy, so it means that you go from here to here. So there is a simulator that given f of x, it samples from this distribution. Okay? So this means that this distribution allows you to recover y, but nothing else. So it contains exactly the information of, that you had by y. In particular, if you apply the function, this function on two inputs which have the same image, then the distribution here should be the same. So the distribution does not leak any information about x. In this sense, this is privacy. Okay? So it keeps the privacy of x up to leaking the value of f of x. And as usual, you can formulate privacy in different ways. So you can think about perfect privacy, when these two distributions should be identical, or statistical privacy, they should be very close up to some statistical error. And you can also think about computational privacy, where these things are only computationally indistinguishable. So they are the same for computationally bounded adversaries. So this is our basic notion. So let's see an example, a trivial example. So the function f encodes itself, right? So this is a silly example. We don't use the randomness at all, but it should be said, right? A function is an encoding of itself in a trivial way, right? You can take the output and decode the original output, just the identity, and simulate by just the identity function. So we're going to be interested in something less trivial, and here's an example for something like this. So imagine that your original function is the RSA function. So it takes x, e, and n, and it outputs x to the e modulo n. Okay? So this is RSA, n is public, e is public. And now consider the following variant of RSA. So it raises x to the power of e, but then it adds a random multiple of the modulus n. Okay? And this is done over the integers. Okay? So I claim that if you take R from a sufficiently large domain, then this thing is an encoding of this thing. Let's see why. So first I can decode. Okay? I can just apply modular reduction and get this value. Okay, this is easy. And I can also simulate, right? So given this value, if I'm going to add a random multiple of n, and this R is taken from sufficient large domain, then this thing will be statistically close to the actual distribution. Okay,
so n is part of the input, or n is a public parameter?
N is a public parameter. I could put it in the output also. So, you know, if I wanted to be someone else would have put it here. I didn't want to confuse it. So E and N are part of the output of the function, and I should put it in both sides. Good. So this is an encoding, and this is actually an interesting encoding. Why? Because you can imagine a scenario when doing modular reduction is too expensive, but doing multiplication over the integers is much cheaper. Okay? In fact, I saw this kind of encoding. I saw it in a talk where people describe the way that they try to implement RSA on the RFIDs, on low complexity devices. And that's exactly what they did. They said, we can't do modular reduction, let's add a random multiple of n.
But don't they need to decode?
They just want to encrypt. So you can imagine a situation where your weak device wants to encrypt, but someone else will decrypt, you know, someone which has more power. Right? So you push the complexity to someone, but to the decoder. This is actually going to be typical in our case. So the decoder will have to work harder.
So if you don't add RN, it's not secure. I mean, it's not.
No. No, if you don't, so it's an easy exercise to see that you leak more information if you just do it over the integers, right? And I did this, you know, this rectangle larger than this one for a reason, right? This thing is longer than this. If you look at the big representation, so this thing is now longer because I did it over the integers, and this again is going to be the typical case. So the encoding is going to output a string which is larger or longer than the original string. Okay, this is again something that, in a sense, is inherent. Okay, so more generally, to use these encodings, so for these encodings to be useful, we want them, the encoding to be much simpler than the original computation. Okay, and this notion of simplicity is going to change depending on the exact application, right? So we can consider different notions of simplicity or efficiency, and each of them will be useful in a different context. And the hope, as in the RSA example, is that, you know, in some situation, and this will be the typical case in the application, we can replace a complicated task by a simpler one, okay? In a way that will going to be the same for us, right? Because this is just an encoding, this substitution is going to be good enough. Okay, just to give another example to get you some intuition of this notion, let me talk about the following application. So imagine that you have a weak device, you know, like your cell phone, and you walked around and you took some pictures, and these pictures are sensitive data. Okay, so this is X, this is private, but you want to release to the rest of the world the value of f of x, some function of the sensitive data. So X is sensitive, but f of x should be public. Okay, that's what you want. So one trivial thing that you can do is just to compute f of x and send it. But if f is too complicated for you, then you are in trouble, right? I mean, you can't compute f of x. So this randomized encoding solves the problem, right? You can just compute the randomized encoding of the function, release it to the rest of the world, and now let them apply the decoder, okay? So this is something that we can achieve. And it's instructive to compare this to the FHE solution, right? So you can use FHE to put your input in a box and send it, say, to Greg. Now Greg can use his gloves, you know, and manipulate this thing and get f of x inside. But now he can't open, right? This thing is encrypted. So FHE does not solve this problem. Randomized encoding gives you an additional thing, right? It allows you to leak some value while FHE hides it completely. And in this sense, I guess that you can say that this is somewhat related or similar to obfuscation, where you can leak something at the end, right? You don't hide things completely. Okay, so we have this object. Let's study its properties. So the first property is composition. Say that you have an encoding of f, and now you encoded the encoding. Okay, so this thing will be still an encoding of f, right? It's the same thing like with string. When you encode the string and then you encode again the encoding, then the new encoding is an encoding of the original string. Okay, so this is also true in this context. Another property is that if you take an encoding of a function f1 and an encoding of a function f2, then this joint function will be an encoding of the pair f1, f2. Again, this is trivial, right? You're just going to concatenate the simulators and concatenate the decoders. But this is very useful because it tells you that if you have a multi-output function, then you can encode it by encoding the outputs bit by bit. Okay? So this is something that you can use. The third property is substitution. So imagine that your function f encodes, so you have an encoding for the function f, and now you plug in some function h. So instead of computing f on z, you compute something, you replace or substitute z by h of x. Okay, and then you do it also for the encoding. Okay, so this new encoding is going to be an encoding of the new function. Let me give you an example to make this clear. So I could present this RSA example as follows. I could say, consider the modular function, which takes y, and just apply the modular reduction. So encoding for this function is just y plus r times n. Okay, so this is an encoding. The reasoning that I gave before showed it, right? And now you can compose this thing or substitute this y by x to the e. Okay, so this is the RSA function overall, and this encoding will be indeed an encoding of the RSA function. Okay? So this is a substitution property, and all these properties have like two-line proofs, right? Especially in the information theoretic setting, but also in the computational setting. Nothing is going on here. Right? These are very simple properties, but we are going to use them again and again, and they will allow us to push basic encodings to more complicated ones, right? To manipulate encodings. Please feel free to ask questions. You know, so quiet.
Substitution is a special case of your composition theorem, right? Plus the fact that identity is a valid encoding or something.
I don't see how, but
because H is not a valid encoding of identity, doesn't matter. Yes, it's still true.
You're saying that this is a special case of this? I don't.
Special case of composition where the outer encoding is.
I don't think so, but we can try to. I don't know. Reducing 3 properties to 2 is something.
Those be 2 different encodings.
I don't see how, but maybe I'm missing it. Okay, so we have these 3 properties, and now we know what it means to encode a function. So let me go one step further and try to encode the function family. Okay, so what does it mean? It means that now my input is not only x and the randomness, but also a description of the function that I want to encode. Okay? So given as a circuit, but you can think about other representations. And this encoding, outputs the encoding of the function c over x and the randomness r. Okay, so this is our encoding. And it will be useful to parse this output into two parts. So the first part, I call it the garbled circuit part, is going to be to depend only on the circuit C and the randomness R. Okay? So this is by definition. I can parse it. I can always parse it like this. And the red part can depend on everything, but typically we'll see at the end that it will depend only on the red part and the randomness. Okay? But this is not something that I require. Okay? So for any encoding, I can parse it like this. And I'm going to think about this part as the offline part and this line as the online part. Okay? And the reason is that imagine that in the morning I wake up and I see this circuit C. So I can toss coins and get the randomness and compute this part. And only in the afternoon I see my input x. Okay? And in this point I can compute x prime based on the randomness that I already have and maybe the circuit that I already know. Okay, so this is why I think about it as an offline and online part.
You don't require that the garbled circuit is non-empty. The offline part does anything.
No, I don't. That's why I said any encoding can be partitioned into these two kind of things, right? It's just I'm looking at the syntax and the syntactic dependency, and that's it. So it can be empty. In fact, I'm going to show you one construction in which it's empty.
You use the word garble in some particular sense, or it's a synonym of encoding?
It's just a name. I need a name. So I'm going to call it like the offline part. Actually, the problem with, so I said, we have many different definitions. The nice thing is that they allow you to think in different ways. But the annoying thing is that we have tons of different, we have terminology confusion, right? So people say garbled circuit, and sometimes they mean this part, sometimes they mean the whole garbling. So there is some confusion. So for me, this is the garbled circuit part.
Why it isn't just an encoded circuit?
You can call it encoded circuit. Because this is what the literature does. I don't like this word either.
I think the point is that you already have this statement there that it says reveal CX and nothing else. Right?
So, okay, but also I didn't say this thing, and I should say it actually. This is relevant to these 2 points. So I think of the circuit as a public thing. Okay, so it's not really, so in a sense it's not really garbled. I'm not trying to hide C for now. I could talk about a variant where you want to hide C as well, and there are quite efficient reduction from one variant to another, and therefore I'm thinking about this circuit as public. So in a sense I agree, this name garbled circuit is not very good. Usually I just think about it as the offline part of the encoding. So I have an online part of the encoding and the offline part of the encoding. Okay. Yes?
Why does it depend on the same randomness?
Because that's how I defined it. I don't know, like that's how construction looked like, and maybe my next metaphor will explain why, okay? But, this is by definition for now, okay? I didn't say that this is inherent, but, I mean, you can always, look at, when you do this thing, look at the first half, the left half, and then using on the right half, but you're not going to do it, okay? And another way to think about this online-offline thing is as follows. So think about this thing as a ciphertext. Okay? So you started by looking at C and you computed some ciphertext. And now given an input X, you can compute a key. So think about it as a key which depends on X. And this key is going to open this lock in a way that will give you exactly C of X. Okay? So it's a strange ciphertext. You compute the C itself, but then given X, you can come up with a key such that the box opens exactly to the value C of X. So the key depends on X. So you see that these two parts should be somehow correlated, and the correlation comes from the randomness. Okay. So I don't know, those of you who are familiar with functional encryption, this looks very similar to functional encryption, and I guess that some people would give their own definition for garbled circuit as saying that this is one-time secure symmetric functional encryption. Right, so I think that you should do the other way around and think about functional encryption in terms of a garbled circuit, but you could do also this. Okay, so this is the notion of encoding a function family. And for now, I'm going to throw away the randomness, so I'm going to make it implicit. And I'm just thinking about this mapping as a randomized mapping. And you have to remember that, it's a shared randomness. So these two parts are using the same random string. Good. So I promised to talk about different notions of simplicity. So here are two notions. So the first notion is affinity. So I want the mapping from x to x prime to be affine. Okay. So this means that if you fix the randomness, then this thing is a degree 1 polynomial in x, in the bits of x. So for example, you won't see here things like x1 times x3. Okay. So there are no such a thing. So this is affinity. You could ask for more actually, and it's useful to ask for more. And sometimes you can ask for that the whole mapping is a low degree polynomial, also in the randomness. So this is the notion of randomizing polynomials, and then Yuval hinted in his talk to this notion. Okay, this is the right notion to work with if you want a constant round secure computation.
With more than two parts.
Yes.
Now your inputs are like some field elements and your circuit is a magnetic circuit, or?
Okay, so you can think, so I didn't specify it, and this is something that I'm going to change. This is going to change during the talk. So you could think about this object as walking over any finite field. Particularly if you want to think of the binary case, think about F2. And this is what usually people do, but I'm going to at some point also to talk about the case of larger fields. So, this notion makes sense over any finite field. Good point. Other questions? The second notion of simplicity is decomposability. Okay, so here I'm requiring that this all garbled input string can be partitioned into blocks, n blocks, such that each block depends on the ith, on a single bit of the original string. So the ith block depends on xi. And again, you can think of x as a sequence of bits or sequence of field elements. Okay, this makes sense. And again, you can require something stronger, namely that each bit here or each element here depends not only on a single input variable, but also on just few elements of the random variables. Okay, so you can require low locality, and this kind of requirement is useful in other cases like parallel cryptography. But I'm going to focus on this main thing. In fact, I'm going to focus on the combination of these two things, which is decomposability and affinity together. So this is decomposable affine randomized encoding there. Okay? So this means that the output here looks like this. Okay? So it means that each block here is computed by taking the product of x1 plus some vector a1, and I'm going to times a1 plus some vector b1. Okay? So this is how the encoding should look like. And again, it's useful to move for a second to the binary case, which is the case that people typically are interested in. So in the binary case, x1 can be either 0 or 1. Okay? So here you'll get either the vector b1 or the vector a1 plus b1. Okay? And going back to the key metaphor, for each bit here you have a pair of keys, a 0 key and a 1 key. Okay? And you're going to output either the 0 key or the 1 key. And previously I said you can think about the whole online part of the encoding as a single big key. Okay, so this key is going to be composed by a vector of keys, which corresponds. So for the first bit, I'm going to choose the right key, and so on and so forth.
I have a question.
Yes.
So you started off by saying that in the first couple of slides, that there is a function f, it's an encoding function g, and then it's simulatable. Did you do any such definition yet for this thing, or?
No. So this is like okay. So I said that that's actually brings an important point. So I define this notion in terms of correctness and privacy. This is my notion of encoding. The function encodes itself, for example. I don't require any efficiency requirement. Okay, this is a well-defined notion. Okay, and it's going to be very useful that I don't put here any efficiency requirements. And now I can talk about different efficiency requirements, okay, or different notions of simplicity. So this is one notion. I gave you like a notion algebra.
That's okay. So you're defining all these simpler ways of encoding.
Uh-huh.
Do a security definition yet? Or?
I did at the beginning, I think. I said, given this, given the output of this thing, okay. So you can simulate this distribution based on the value of C of x, right? For any x. That's the security definition.
Clean, like this is an encoding of f, this is an encoding of g, something like that.
Why not?
Also, the function you're defining is just output Cx.
Maybe I was asking if the simulator is efficient or not. Or
No, not that. I mean, what is this? I mean, this is a mapping. Is it encoding of some
Yes.
function? Like just Cx?
Yeah, the function C. So I have the description of the function. So this description is public. So for example, I'm allowing the simulator to depend on it and the decoder to depend on it. And you know, this thing outputs an encoding of the function C. So I could also define it as I could also break this thing into two parts. I could say, I want a compiler that looks at the circuit C, say, or description of a function, and then it outputs to me the description of the encoding of this function. Okay, this is something that you can do, and then people have done. But I think that this view is simpler, at least to put on PowerPoint slide. Okay. Good. So you know, so I'm kind of switching between different ways to look at it. So you know, it's good to look at it just as a affine mapping, but it's also good to have these keys in mind because we're going to use this view as well later. Good. So let's start with the feasibility results. So I'm going to talk about old feasibility results like Yao and other things, but I'm going to present them using a relatively recent framework that we presented together with Yuval and Eyal. So let's start with the perfect security. Okay, so I want a perfect security, a decomposable affine randomized encoding. I'm going to show you in a minute how to do it for formulas or even arithmetic formulas. And the caveat is that these keys may be long. Okay, so usually when you think about garbled circuit, these keys are short, but I'm not requiring it. Okay, all I want to do is having this affine form, affine decomposable form. This is already non-trivial. Okay? Think about a function which is a high degree polynomial. It's not clear how to represent it in this way. Okay, so this is our goal. And let's start with some toy examples. So say that I want to encode this function. So this function is already affine, so it looks easy, but it's not decomposable, right? It has a single output, and this output depends on both inputs. So I have to do something, but I don't have to work hard. So I can output an encoding which has two outputs, okay? And I'm going to pad or mask the first input in the first output, and then I'm going to give you x2 minus r, okay? And this, I wrote that R is chosen from a finite field, so think of all the addition as working over a finite field. If you want to think about the binary field, okay, this is a special case. And it's not hard to see that this is a valid encoding, right? I mean, how do you decode? You just add these two things together, the R cancels out, and you get x1 plus x2. On the other end, this thing reveals no other information. So in particular, the first entry here is uniform over the field. And the second entry, well, it's just a random element subject to the correctness constraint. Right? So I can easily simulate it just by outputting a random value and given the output, subtracting this random value and getting this thing. Okay. So this is this was easy. Let's look at something slightly less trivial. Let's look at the product of two things. So this is not a affine, right? This is a monomial in x1 and x2, and I want to encode it by a decomposable affine randomized encoding. So how can I do it? So let's start. So let's start just by masking x1 and x2. Okay, so this makes sense. So far I didn't give you any information, so I didn't lose anything. But now I have to give you some information that will allow you to recover this monomial. And if you think about it for a minute, you'll see that there's a simple way to do it. Just give all the degree 2 monomials except for the one that you want. Okay? And now you can, in order to decode, you can take the product of these two things. Okay? And now you get all 4 monomials, subtract this thing, and you will learn the monomial, the missing monomial, right? x1 times x2. And again, privacy is easy to argue, right? This is uniform, and again, this is uniform subject to the correctness requirement. So this is nice because this is affine, right? I mean, all the x1, all the x's appear as a degree 1 terms. But this is not decomposable right now, but it's easy to make it decomposable. And we can take this last entry and just break it into 2 like we did here. So let's add a new random input and just break this thing into plus R3, minus R3. Okay. So it's not hard to prove that this thing is an encoding of the original thing directly, but let me show you how to use these properties nicely in order to prove it. So we know that these two guys encode this thing, right? We already proved it. And we know that this encodes this and this encodes this. This is trivial. This is the same function, so a function encodes itself. And therefore, the concatenation of all these guys encode the concatenation of all these guys. And now I use this composability. So if this thing encodes this one and this thing encodes this one, then this encodes the original thing. Okay? So you can easily argue security by using these simple properties. Okay, so you could do, okay, so this is like a vector representation of this encoding, so you can just write it like this, exactly like in the previous picture of a decomposable affine randomized encoding. So you could do similar tricks for any finite monomial or any finite polynomial. And in particular, I'm going to be interested in this specific degree 2 polynomial, which takes x1 and takes the product with x2 and adds x3. Okay? And you can tweak the previous encoding to get this encoding. Okay? And I'm going to call this thing the affinization gadget. Okay? So why it takes a degree 2, a specific degree 2 polynomial and make it into an affine, and get an affine encoding for it. Okay, so we have encodings for finite functions, but let's try to, to do something for more general functions. So let's try to work with circuits. And I'm going to write this circuit as a layered circuit, so it has layers. This is the input, this is the output. And I'm going to gradually encode this circuit. I'm going to do it in a kind of a strange way, so I'm going to go from top to bottom. Okay? And in the ith step, I want to encode the function that maps the ith intermediate value to the output. Okay? So eventually, when I get down, I will be able to encode, the function that takes the input to the output. So this is good. So I'm going to start from here and extend my encoding downward. So the first step is trivial, right? I want to encode the function that maps this intermediate value to the final out value, but this is just the identity function, so I can encode it easily. This is a decomposable affine randomized encoding for this function, trivially. Now let's assume that I got to this level. So I have a good encoding for the computation that takes this thing to the output level. And I want to extend it to encode the function that takes these values to the output. So how can I do it? So let's look at this value. This is just the product of these two guys. So I can use substitution and replace this thing by the product of these two guys. And similarly for all these things. So this is a valid encoding, right? I mean, we know that this is encoding. The problem is that it's not affine anymore. Okay? It's a degree 2 in the variables. But now I can look, vertically, horizontally on each of these bits and think about it, as a degree 2 polynomial, and then apply the affinization gadget. Okay? So notice that these vectors grow. My affinization gadget started with a single output and gave me a longer outputs, but okay, you have to pay somehow. So this is affinization. I can continue doing it level by level until the end of the circuit. So what do I get? So the key length is going to be exponential in the circuit depth. Therefore, I get perfect decomposable affine randomized encoding for functions which has logarithmic depth circuits. So this is like a new proof for the IK00 and 02 results. Actually, they showed something stronger. They had the encoding which achieve a constant degree also in the randomness, actually degree 3. And they could also work with slightly stronger functions. But it gives you a flavor of what can be achieved. So note that, by the way, that it works for arithmetic and C1 circuits as well. Right? So all the gadgets that I used, they were arithmetic, so you can work with arithmetic formulas. And this raises the question, which is closely related to the things that Yuval mentioned. Can you get perfect decomposable affine randomized encoding for circuits? Okay, for general circuits. In fact, forget about circuits, do NC2. I will be happy. Okay? So this is, I think, a wonderful question. We don't know how to solve it. And if you solve it also with a low degree, then you'll solve a Yuval problem about information theoretic secure computation 4P with constant rounds. Right, so fascinating problem. Solve it, or where is Evgeny? Or find a reason to believe that this is unsolvable. Yes?
So if you remove decomposability or fineness or perfect, I mean, is it known?
Yes. So if you remove perfect, it's known. That's the next point.
Computational, statistical.
No. We don't know anything. Like I wrote it in this formulation, but even relaxations of this thing, we don't know. Like if you remove, you have to be careful. If you remove decomposability and affinity, then the function itself encodes it. So you need some notion of simplicity. I don't know any reasonable notion of simplicity for which we have information theoretic encoding for all P.
For NC3, NC2 might be simple, right?
I don't know. Like it would be wonderful. I think that right now we have no idea of how to go over, say, log space. Right? This is what IK gives us. So it's slightly over NC1. It's log space or non-deterministic log space. But going, say, to NC2, I don't know. Okay, so we can't get the information, we don't know at least how to get information theoretic encoding for general circuits, but what about computationally secure encoding? So, this is the second best thing. So,
I don't know if you're going to show, but I don't get a good sense of why decomposition is so important.
I can tell you, I didn't plan to show it, but okay, since you asked. Okay. So you see, so this is decomposability. So think about Yao's protocol. So Yao essentially used this decomposability property in order to reduce the secure computation of this function to an OT. Right, so again, as I said, where were the keys? Okay, good. So for each input you have the 0 key and the 1 key. So you can use OT to send the keys for the other party depending on its input, and therefore you can reduce the computation of this thing to OT. But there are also other reasons. It turns out that this decomposability pops again in several different contexts, and it's useful.
Yeah, I was hoping for a more abstract
answer.
Beyond this particular, I mean, clearly it's a useful thing to have.
Locality is important.
Locality.
I mean, in a sense.
Local, right? It's not as opposed to a global linear function. OT is something you can see from.
Yeah.
I would say that anything think about the original computation. It's a complicated computation. You do all these things with the circuit. I think that anything that will make this thing, so this is the dependency on the input in the new thing. So anything that will be much simpler in some sense, I think. Choose your own thing, but it will be much simpler than the original computation is already non-trivial. For example, you could relax decomposability and then like the FKN model. So imagine that, forget about bit decomposability, but you could say that you can think about the left half and the right half of X, and the part of the encoding that depends on the left half depends only on the left half, and you have the encoding that depends only on the right half. This is a weak notion of decomposability. It's still useful. So in any way that you can simplify this computation compared to the original one, I think that it will be interesting.
So you could view it, I guess, as a reduction from computation of C of X to computation of the online part, right? So
Yes.
the online part is easier.
Yes, that's the original thing that was the original motivation in a sense to this notion. Okay. So we said that we don't know how to get perfect security for circuits, but let's try to do it to get computational private encoding. So let's go to the previous construction and see what goes wrong. Okay, and it turns out that you can fix what goes wrong by using this so-called key shrinking gadget. So let's see. So what did we do? We encoded the circuit from top T to this point. We did a substitution. Nothing happened. And then we did affinization, pop, the keys go, right? I mean, the vectors become very long. So if we had a way now to apply this key shrinking gadget, which shrinks this vector, possibly at the expense of increasing this offline part, then we would be in good shape. We could continue this process again and again and again for many, many layers. So this is exactly what we need, and formally what we need is again an encoding. So we want to be able to encode a long affine function by a short affine function. Okay. And you're allowed to also increase to put some offline things here. And note that I'm allowing these short vectors A and B to depend on C and D, and maybe the randomness, and also W, but they're not allowed to depend on Y. Okay, so this is the gadget that I need. And again, if you think about it a little bit, once you define this thing, you can see that it's actually not hard to implement it, at least in the binary case. So how do you shrink keys in the real world? Question mark?
Yeah.
What?
PRG?
PRG, or more abstractly, you use symmetric encryption, right? You can encrypt your long keys by using short keys. So that's exactly what we're going to do. So in the binary case, let me be more concrete. We have two cases. If this y equals to 0, then the encoding should release D. If y equals to 1, then the encoding should release C plus D. So there are two cases. So let's just encrypt D under the key B. Okay, so if y equals to 0, then you get the key B and you can open this encryption and learn D. And let's encrypt C plus D under the key A plus B. Okay, so if y equals to 1, you get this key and you can open this box. Okay. So this is my encoding up to minor cheating. Okay, so this is what I'm going to do. So there is a tiny issue here, which is how do you know which box to open? Say that you get this key, how do you know which box to open? So this can be solved easily. Just use a new random bit to permute these boxes, okay, toss a coin and give and release the value of y XOR this bit. So this will give you a pointer to the right box. But up to this technicality, this is the encoding that we're going to use. So great, that's what we needed, that's what we have. Proving that this thing is private is very easy. Correctness I just show you. So as a corollary, we get Yau's theorem, right? We get that we can get decomposable affine randomized encoding for general Boolean circuits from one-way functions. We used only symmetric encryption, so this can be based on one-way functions. It's actually online efficient. So the length of the key is n times lambda, where lambda is a security parameter. It's independent of the size of the circuit C. And we get computational privacy. And this is somewhat, I guess, a non-traditional way to view Yau's protocol, so or Yau's construction. Typically, we talk about locks and boxes for each gate, and this looks, I don't know, in a more modular way in this construction.
Why is it times lambda? So we can just see because for each bit you get.
Eventually, when I'll finish going down, I'll get for each input here, I'll get this vector, which whose length it depends exactly on the security parameter. Good. Okay, I should mention here, so two other results that I'm not going to talk, but there are extensions of these theorems. So first, you can get low degree encoding and low locality, constant actually, if you assume that you have a log space computable one-way functions. So, and this is again relates to what Yuval mentioned, that this allows you, for example, to get under this assumption constant round secure computation for P. We actually know how to do it from one-way functions without going through this way using the BMR construction, but still it's a very clean way to do it. And also, recently it was shown how to extend this theorem to the RAM setting. So get it under one-way function. So there's a sequence of works, and I understand that Daniel is going to talk about it tomorrow. Or is Daniel? Yes, okay. So we will hear about it tomorrow and also in the next workshop, so I'm not going to mention the details here. Good. So let's move to the arithmetic setting. So now let's assume that our circuit is an arithmetic circuit. So it means that the gates perform addition and multiplication, and this input comes from some finite domain with algebraic structure. Think about a field. Okay? And think about this field or domain as very, very large, super polynomial, maybe exponentially large. So we'd like to get the analog of the randomized encoding in this setting as well. And the motivation here is both by efficiency and feasibility. So in terms of efficiency, it's true that you could take this circuit, compile it, into a binary circuit as usual, and then do the encoding. But this will typically be less efficient, right? Because you have to implement this multiplication addition gates in a binary way, and depending on the field, it can be expensive. In addition, you can think about it as a question of arithmetic feasibility. Again, thinking in the MPC language, think about players which are all arithmetic, so they're all arithmetic circuits, and they want to compute arithmetic functionality. Can you do secure computation in this world? Okay. So the BGW protocol, for example, works with the arithmetic circuits, all arithmetic players. Fine. Okay. So let's try to use our previous template to solve this problem. So everything works well. I mean, all the gadgets that we used were information theoretic and they work over general field, except for this key shrinking gadget. Okay, so all we need to do is to implement the key shrinking gadget. And there's, an obvious generalization of what we did before. Okay, so I could release boxes for each value of y. Okay, so if y equals to a 0, I'm going to give you an encryption of d under b. If y equals to 1, encryption of a plus b under of c plus d under a plus b, and so on and so forth. So you need some related key security for this thing to work, but forget about this. Before talking about security, this thing is simply not efficient, right? I mean, you cannot go over all the elements of the field if the field is too large. Right? So this is a problem, so we need something more clever to do. we need a way to compress all this ciphertext. Okay. And now let's turn to our public key friends, and let's assume that you have this nice encryption, symmetric encryption, but with these strong homomorphic properties. So what do I want it to do? So I should be able to take a linear combination of this ciphertext, and somehow get a linear combination of the messages encrypted under the linear combination of the keys. And this is the kind of homomorphism that I need. If I get this thing, then I'm in a good shape. Why? I can take the linear combination of this thing, learn the ciphertext, and now use the key. I have the key for this thing, and open it and get this YC plus D. Okay, so this is essentially what I need. And what we show in that paper is that you can approximately achieve it over the integers using LWE. Okay, so not really this thing, but something in this flavor. Okay. So as a result, if you plug it in the previous template, you can prove that there is a decomposable affine randomized encoding for arithmetic circuits from LWE. So it's going to be online efficient. It works over exponentially large integers, but the decoder is a Boolean, so it's not arithmetic. And if you think about LWE, decryption typically involves rounding, okay? And this is not an arithmetic operation. You can still ask, can you get a decomposable arithmetic randomized encoding for circuits over general finite fields? Okay, so this works like over the integers. And together with Avon and Bozuska, we show that this is impossible if the decoding is also arithmetic. Okay, so you can't get online efficient arithmetic randomized encoding if you require both the encoder and the decoder to be arithmetic. Still, there's some gap between this impossibility and this feasibility result. And you can ask, say that I'm allowing the decoder to be a Boolean, can you get it over finite fields? Okay. So this is still open. I don't know so our impossibility result strongly relies on the fact that the decoder is arithmetic. I don't know how to extend them to the case where the decoder is Boolean. So I think this is an interesting question.
Well, how do you show impossibility?
So actually the impossibility, I think that it's, so I'm very proud of this result. so somewhat unexpectedly, you use tools from arithmetic complexity. So you use partial derivatives in order to attack. So you actually prove an attack, give an attack about schemes like this. And the intuition is as follows. So I didn't define exactly what it means to be arithmetic, but assume that your encoder and decoder works, with like a black box access to the field. So this means that it should work even if the field is very, very large. So I'm going to choose a field which is much larger than the size of the circuit. In fact, if you look at the degree of the circuit as a polynomial, okay, the characteristic of my field is going to be larger than the degree of this polynomial. And now, when you have a polynomial, a low-degree polynomial over a large field, you can do all sorts of things. Right? I mean, and we use this. So just for intuition, we don't use it. But for example, you can check if two polynomials are identical, whether they compute the same functions, right? Just by using Schwarzschild. Right? Something that you can do in the Boolean case, right? You can check whether two circuits compute the same function. This is CoNP complete. So we don't use this property, but we use other things that happen when the field is sufficiently large, and we can show that we can attack this thing. So I think that this is actually an interesting result, and the reason that I think that it's interesting is because it also extends to like fully arithmetic MPC. And the reason that I think that the fully arithmetic MPC is interesting is that it turns out, I think that most information theoretic constructions that we have are typically arithmetic, like think of BGW or things like that, think work with polynomials. And we don't know any impossibility results for this kind of thing, so this may be a way to prove some limited impossibility results for information theoretic constructions. Like if an information theoretic construction is arithmetic, happens to be arithmetic, then the lower bounds kicks in. So that's why I think that this result is interesting.
When you say that the decoder is arithmetic, you mean arithmetic over this exact same field as the encoder?
Yeah, so I'm thinking of, all honest parties have, so there is a formal definition, so all honest parties have an access to a field oracle. When I'm going to do addition, multiplication, inverse, check if something is zero, and other things.
Important that it's the same field over which you do the encoding, or is it?
Yes, so I assume that the function is yes, yes. I'm not sure even have to formulate it with with different fields, but like in my thing, I'm thinking of the adversary as choosing the field and give it to everyone, like give the oracle to everyone.
So the impossibility breaks down if the construction knows the size of the field.
Good question. So yes, so the question is it has two parts. So yes, but note that in the context of finite fields, if you know the size of the field exactly, that you know the field. Okay, so you know everything. It's an interesting question to ask whether the impossibility result still holds if you have an upper bound on the size of the field. Okay, so this I don't know. I suspect that we can extend the impossibility result to this model, and in fact this model is interesting because Yuval Manoj and Damit have a paper that uses this model essentially when you have some bound on the upper bound on the size of the field.
And do you think that this extends to rings?
Wow, I don't know. Impossibility result for fields, so in terms of algorithm, so you can't even do fields. So why would you be able to do rings? I don't know. Like a field is a ring, right? So for impossibility result, yes.
Possibility. I mean, so you're using for the possibility result, you're using some sort of a norm, right? I mean, you're using LWE. So.
Okay.
So Danny, I don't know if you tried this 11. So this new simpler FHEs from LWE, would they help you to do this key shrinking? I mean, did you try to improve it, or you think you're kind of...
I didn't try to improve it. Maybe, I don't know. I mean, it will be interesting. I think if I was brave enough to try to implement things, then I should have looked at it, at least a ring LWE, but I didn't.
Exactly, so integers, right?
Yes, but you can reduce in a non-black box way large fields to integers, so it will allow you. So actually, you can hope that this thing will be useful in practice, and if you believe this, then trying to find the best gadget is actually an interesting question, because all other parts are actually very efficient. Okay. So summary so far. So we have this general template for getting a garbled circuit. So it's alternative to Yao's original presentation. It's in a sense independent of the domain size, and it gives you modular and simpler proofs, both for a computational setting, in the information theoretic setting, and in the arithmetic setting. Okay. So this is kind of the second part of the talk. I'm going to talk about efficiency improvements. And then I will try to address three questions. So the first question is, can we compress this part? So can you get very short online garbled input? The second is, can you reuse this offline part? And finally, can you optimize the time complexity that it takes you to compute the whole encoding? Okay, can you do it very efficiently? So these are the three obvious questions. There are probably more. So let's start with the first one. So I can define the online rate as the ratio between the length of the garbled input to the original input. Okay? And in Yao's construction, the rate is lambda. Okay? So for each bit here, you're going to put a key, right? A cryptographic key. So you pay a factor of lambda. This is a security parameter. And you can ask, what is the best achievable rate? Right? Can you go below lambda? And what we show, and this is a joint work with Yuval, Eyal, and Brent Waters, we show that assuming any of these assumptions, so essentially all the standard public key assumptions, you can get a affine randomized encoding with online rate 1. Okay? In particular, the length of x prime will be the length of x plus the security parameters. And some of these constructions, I think, are actually practical. Okay? So like a single DDH element. The time complexity will be quasi-linear time, so it will take you n to the 1 plus epsilon for an arbitrary small epsilon to compute this online part. And note that here I wrote affine randomized encoding, a non-decomposable affine randomized encoding, and in fact decomposability is impossible for this kind of rate. Okay? So I had to...
What do you mean by decomposability?
So decomposability, it means that the online part can be decomposed to blocks, where each block depends on a single input of the...
It's like that every input bit selects one of two keys.
Right. Still, for secure computation, if you have affinity, then it's good enough. You can do. It's very easy to get secure computation using affinity alone. Yes.
You go
for the weaker decomposability where, you know, there's just two parts and each one of them is encoded separately?
I didn't think about it. I would assume, I'll show in a minute a different extension where I'll try to break this thing, but you'll get a similar bound. Yeah,
I mean, in which case is it impossible?
I just said that it's impossible to get also the decomposability. So if you want decomposability, you have to pay something which depends, like order of n times lambda, or you know. Yes, yes, yes. So essentially, for decomposable, the previous construction that we had is optimal. That was my answer.
So here axis you view it as a bit vector, so it's like affine. I mean.
Yeah. For now, x is just a vector of bits. So I'm going to show you the construction in a minute. You'll see. I have n bits here. I'm going to send n bits plus a key.
Sorry, so I mean, it's, if you didn't care about affine, it's possible trivially, right?
Right. So I'm going.
Where is the?
I'll talk about it after the construction. I'll talk about it. Okay. So I want to prove this thing. I'm going to steal a few minutes from the break, and then we'll just shorten the second part. So I'm going to show you how to prove this, and I'm going to introduce this gadget, set encryption, which is kind of cute, and then I'll show how to base the theorem on this gadget, and later I'll show you that, again, this gadget reduces to some form of key homomorphic encryption scheme. Okay, so this is the plan. So what is set encryption? So consider the following story. So Alex wakes up in the morning. She has all these files, right, videos that were recorded at Simon's. She encrypts them and sends them to Bob. Okay? And then in the afternoon, she decides that she wants to reveal a subset of the files, a subset of the messages. So she's going to send this subset plus a single cryptographic key that will allow Bob to learn exactly these messages. Okay? And it's crucial, I'm going to require that the length of the key is lambda, namely the security parameter, and it's independent of the number of messages. Okay? So if you know broadcast encryption, this is kind of the dual form. I want to open a subset of the messages, not to open a subset of the receivers. Okay. So this is our gadget. I'll show you later how to construct it, but for now let's assume that we have it. Okay? And now here's a construction of online optimal garbled circuit. So I'm starting in the offline part, so I have my circuit. I'm going to construct the standard garbled circuit with all these pairs of keys. Then I'm going to choose this random vector. It's an n-bit vector, and I'm going to permute each pair of keys depending on this vector. So if the first bit here is 0, I'm not going to permute the pair. If the second bit is 1, I'm going to permute this pair. Okay, so I kind of shuffle the keys based on this n-bit vector. And now comes, and I'm going to throw these keys into this gadget. So Alice is going to encrypt all the keys, and this is my offline part. Now comes the online input X. I'm going to XOR it with this set. So this defines a subset of the keys that I want, and I'm going to generate the key that corresponds to this subset. And that's it. So that's my encoding. So note that the online part is just n bits plus a single key. Okay? How do you decode? So the decoder will use this key and this subset to open the cells that correspond to this set. Okay? These are exactly the keys that I want him to open. Okay? These are the keys that correspond to X. And now we can do the decoding procedure of the garbled circuit and learn C of X. Okay? What about security? So simulation is kind of obvious. So you'll start with the Yao simulator to get the garbled circuit part and these keys. Right? Now you're going to throw these keys into random locations. Okay? And put garbage in the other cells, and you can generate this subset, random subset, and the corresponding key using essentially the semantic security of the previous encryption scheme. Okay, so this is the construction, n bits plus a single key. So now I want to implement this set encryption gadget, and the idea is to use this symmetric encryption, which again has some form of homomorphism for both keys and messages. In particular, imagine that I can take a first ciphertext, which was encrypted under the first key and some message M, and the second ciphertext, which encrypts a second message under a second key, add them together and get a ciphertext of the sum of the messages under the sum of the keys. Okay, so this is the gadget that I want, and we can implement it, or variants of it can be implemented under DDH or LWE. Actually, for RSA, we have to do something slightly different, but we can also solve this problem. Okay, so given this homomorphic encryption, how do I construct the gadget? So Alice wakes up in the morning, she has all her files. You're going to put them on the diagonal of a matrix. And all the other entries of the matrix are zeros. Okay? And now she's going to encrypt each column separately under fresh keys, independent keys. Okay? And she sends it to Bob, the encrypted matrix. And now comes the afternoon, right? And we have a subset of the keys, a subset of the messages that Alice wants to reveal. So she's going to add the corresponding keys and send this thing to Bob. Now Bob see this subset, he can add together the corresponding columns, so in this case C1 and C3, right, the corresponding ciphertext. And now we can use this key, this combined key, in order to open this ciphertext, and we get M1 and M3. And since we put them on the diagonal, they will not mix up, and we'll get the messages as we wanted. And so that's the construction.
So this is relatively heavy. I mean, you don't care about offline part, but you pay quite a bit in the offline part.
Good. So I knew that you will ask it. So quadratic, right? A lot. So first I can reduce it to, if you do it on small parts, you will reduce this quadratic overhead. Second, for the RSA solution, you don't pay this quadratic thing. So you do something else, and you don't have this overhead. But you can also, I think that it's a legitimate answer to say that, on the offline part, I'm willing to pay a little bit, right? I mean, think of this compared to the whole garbled circuit, which depends on the circuit. So in the typical case, the circuit is so large anyway, that this overhead is not an issue. But you can reduce it.
So this LWE thing, I don't know, just syntactically, it looks exactly like this thing from Daniel's talk, this doubly homomorphic trapdoor thing. Is it related, or?
I'm not sure. You should ask Daniel. I don't know what.
Answer all your questions tomorrow.
Right. I promise you that tomorrow in Daniel's talk you'll hear about garbled circuit, LW, obfuscation, and RAM. Okay. Now I don't know. I didn't read their paper. I don't know. So you know that here the homomorphism is kind of over the keys and the messages simultaneously. I don't know. Typically in homomorphic encryption you don't talk about the keys, but maybe I don't know. You should. But since I can get it under DDH in a very efficient way, why would I? Okay. So a few more slides and we'll take the break. So we do get online rate 1, okay? And you can ask, is it optimal? So maybe you can go below 1, right? Maybe you can compress this m-bit string into something which is shorter than n. This will be even better, right? So one observation is that if you define these two things to be independent, so this x prime is independent of the circuit C, but the randomness is common, then this is impossible. Why would it be impossible? So imagine, this is by the way how Bellaire et al. Define a garbled circuit. So in their definition, this thing should be independent of the circuit. So it should be, it will be impossible to consider all the circuits will just output the RF bit of the input. Right? So this thing should be a valid encoding for all these circuits, and you simply, in terms of information, you must be wrong on at least one of them. Okay? So you can go below n if this is the case. Still, you can ask, maybe you can do something better in a different model. So consider the following model. Let's say that this x prime depends on the circuit, but to make this question non-trivial, I have to assume that the circuit is short, right? It has a short representation, so let's assume that this is a Turing machine. Okay? And again, to make this thing non-trivial, like if I can compute the function by myself, then I can just put it as C of x. So. So I have to assume, to make the question non-trivial, that the time that it takes to compute the encoding is smaller than the time that it takes to compute this function. Otherwise, again, you can put it just C of x, it's a single bit. So let's assume, for example, that that it takes the time that it takes to compute the function is n cubed, but the time that it takes to compute the encoding is n squared. Can you do this kind of thing? Can you get in this setting?
You're already requiring that the encoding is in some sense simpler than computing the function. So why do you, in addition to that, needs to?
No, so I just threw away these requirements, right? So I have to put some requirement. So here is a new requirement. Can you do in this setting? Can you go below? Okay. So I could talk also about affinity as a requirement, but I threw it away because affinity you can also show easily that it's impossible. So So I threw away affinity. That's actually I didn't say it. So. Okay, but in this setting, this is like the most liberal setting that I can think of in which this bound can maybe achieved. So if I had this kind of encoding, then it means that C is a compressible function. So what do I mean by this? So it means that the complexity of the function is n cubed, but some weak guy who runs only in n squared time, can somehow compress his input from n bits to something smaller than n bit in a way that will still allow you, someone stronger than me, to do the computation. Okay? So this notion of compressibility was used by Harnik and Naor, later by Dubov and Yuval. And so we can see that if you get such a garbled circuit, then you get a function which is compressible. And recently we showed, this is together with Fomenko and Kwang and Shaltiel, that actually incompressible functions are likely to exist. So under complexity assumptions, things like Nissan-Wigderson and complexity assumptions which are related to de-randomization, can actually prove that there are functions which run in time n cube, such that any n squared player will not be able to compress the function below n bits. Okay. So this means that if you believe these assumptions, then rate below 1 is unlikely to be achieved.
Okay. What are the assumptions?
So the assumption will say, so the Nissan-Wigderson standard assumption says that, that basically non-uniform model cannot speed up the uniform model. So E, like 2 to the n time Turing machines, cannot be computed by circuits which are essentially sub-exponential. So you have to strengthen the assumption a little bit by assuming this also for circuits which have, say, gates to, which are, say, non-deterministic circuits. This is actually enough for us. Or circuits which have gates to, I don't know, sigma 1. So it's something that people in complexity use from time to time. This is, for example, the kind of assumption that they use in order to de-randomize the AM or things like this. So, but basically, it's an assumption about the relation between uniform complexity and non-uniform complexity, plus some limited non-determinism. Okay, so I think that it's a good time to take a break.